Okay. So, we derived an expression for the flux with respect to Matano interface, and that expression is given by this NV C 1 minus C V 2 dou mu 2 by dou x minus V 1 dou mu 1 by dou x. I am going to write it by doing a little bit of algebraic manipulation, and the expression that I am going to write is like this. So, NV C into 1 minus C, so that part I am going to keep. Then I am going to write this 1 minus C times V 2 plus C times V 1. This entire thing is multiplied by dou mu 2 by dou x minus dou mu 1 by dou x, okay, plus V 2 minus V 1, okay, C times dou mu 2 by dou x plus 1 minus C times dou mu 1 by dou x. Okay. So, this is a simple algebraic manipulation. You can do the algebra and show that it comes back to this expression. You can check it for yourself. The reason why I am doing that is that, as you might have studied in your material thermodynamics course, C times del mu plus 1 minus C times del mu 1 is equal to 0 by what is known as the Gibbs-Duhem relationship. Okay. The reason why we modified this expression and wrote it in this form is to make sure that this part goes away, because by Gibbs-Duhem relationship we know that any term that has C dou mu 2 plus 1 minus C dou mu 1 is going to be 0, right. So, what are we left with? We are left with only the first line of this modified expression. So, let me write that expression. I am going to make a simple modification. So, I am going to say that NV times C times 1 minus C times 1 minus CV2 plus C times V1, I am going to call that as, so let me keep the NV. So, let me call C into 1 minus C times 1 minus CV2 plus C times V1 as the mobility, and this quantity dou mu 2 by dou x minus dou mu 1 by dou x. This is the diffusion potential and this is the mobility times NV. Okay. So, where, okay, obviously I have written all this as M. So, M is nothing but C times 1 minus C times 1 minus C times V2 plus C times V1. Okay. So, this is how we have defined, and so let us proceed further. Okay. So, we have obtained an expression for J in terms of mobility and gradient on what is known as the diffusion potential. Okay. So, what is the diffusion potential? Because N V times mu 2 minus mu 1 is nothing but dou G by dou C. Okay. So, we are going to use this expression, because remember the expression that we derived said that J is equal to minus N V times M times dou mu 2 by dou x minus dou mu 1 by dou x. Okay. So, mu 2 minus mu 1 is nothing but 1 by N V dou G by dou C. So, this N V times mu 2 minus mu 1 if I can take, then I can see that this is nothing but minus N V M. Okay. So, N V I am going to absorb. So, that is nothing but M times dou by dou x of dou G by dou C. Okay. So, I am going to do one more manipulation. So, minus M, this is d by dx of dou G by dou C. So, I am going to write that as dou del square G by del C squared del C by del x. Okay. So, instead of acting dou by dou x on this quantity, I am going to say that dou by dou x is nothing but dou by dou C into dou C by dou x. So, dou by dou c acting on this is going to give me del squared g by del c squared, and so dou c by dou x. Okay. So, what did I do? I replaced this operator by dou by dou c and dou c by dou x, I multiply. Okay. So, instead of dou by dou x operating, I made it dou by dou c operating on this. Because of that, I had to multiply by dou c by dou x. So, this is what I have done. So, let me give a shorthand notation. So, this is minus m, let me call this as g double prime, which is what we have been calling, because this is nothing but the second derivative of the free energy with respect to composition, right. Free energy versus composition curve, if you take the second derivative, this is g double prime, which is what defined this spinodal point, obviously, right. That is the reason why we are interested in this. This becomes negative, or this becomes positive, or this becomes 0, wherever this becomes 0 is actually the spinodal line. So, we have dou c by dou x, that is j, right. So, this is the expression that we have. So, now we are going to derive. So, once you have the expression for j, we know that dou c by dou t is equal to minus 1 by n v times dou j by dou x. Where does this come from? This comes from the mass conservation, right. Previously, when we were talking about composition, there were no NV factors. Okay. So, this number of atoms per unit volume or per mole quantity, this NV will always appear in this type of derivation. They do not appear in the usual Fick's law. The usual Fick's law, it said dou c by dou t is minus dou j by dou x, right. But this NV is there because we are now discussing about chemical potential, which was defined per atom. So, this NV is going to keep appearing everywhere. Now, let me put this j into this expression. So, what do I get? I get an expression for the rate of change of composition in terms of the concentration gradient, which is what the usual Fick's law is. So, let us do that. So, j, which is equal to minus m g double prime dou c by dou x, we had this expression, and dou c by dou t is equal to minus 1 by n v dou by dou x of j. So, I am going to put this quantity here, minus m g double prime dou c by dou x. So, minus and minus is going to become plus. I am going to assume that m and g double prime are constant, because I am going to take this dou by dou x here. If I assume that they are constant, then I get m by n v g double prime del squared c by del x squared. Okay. Assuming, this is very important, the mobility m and the g double prime are constant. What is g double prime? This is the curvature of the free energy versus concentration diagram. Okay. So, this is dou c by dou t. Now, let us compare with the usual diffusion equation. What that say? Let me say that that is some d times del squared c by del x squared. If you compare these two expressions, you see that diffusivity is connected to the mobility, some number of atoms information is there, through the second derivative of the free energy curve with respect to composition. Now, spinodal region, right, we had the free energy versus composition curve, which was like that. Spinodal is the region where g double prime is less than 0. So, because g double prime is less than 0, mobility is positive, Nv is just a number which is positive. So, diffusivity becomes negative, right. So, this implies that if g double prime is less than 0, then d is less than 0, right. So, in the other case where g double prime is positive, you can see that the diffusivity is positive. So, Fick's law happens to be a special case, right. When we are writing in terms of diffusivity, we are really not worried about the sign of g double prime, because that works in regions where g double prime is actually positive. When g double prime becomes negative, then the diffusivity has to become negative, right. So, we discussed this in one of the earlier modules. We said that the diffusivity becomes negative whenever there is an uphill diffusion, right. Now, this derivation that we have done, identifying the diffusivity in terms of the mobility, shows that diffusivity and mobility are connected through the second derivative of the free energy with respect to composition. So, obviously, the sign of G double prime is going to define the sign of diffusivity. So, from this derivation, you can understand why suddenly diffusivity will become negative under certain circumstances. It depends on what kind of free energy versus composition curve you have in your system, right. So, this is what the relationship that I used in one of the previous modules when I was deriving the relation between the amplitude of a sinusoidal composition, which was put as a solution to the diffusion equation, to this the same equation, and we said what happens to such sinusoidal composition fluctuations. There I introduced this relationship between diffusivity and mobility, and this is how this relationship is derived. Okay. So, we were trying to look at a solution of this equation by putting a times exponential I beta x kind of solutions, and where a was dependent on the beta and time. So, there I introduced this expression, and this is the origin of this expression. So, we have derived how this D and M are related to G double prime, which automatically explains as to why in the spinodal region you expect the diffusivity to be negative. Okay. So, in the next part we will go back to the expression that we derived for the amplitude or rate of change of amplitude and see what happens to it as a function of beta, which is the wave number, or the lambda, the wavelength, which is the inverse of beta, and discuss what happens in the spinodal region. Thank you.